Hello and welcome to the demonstration of the CAE workflow for warpage prediction of additive manufactured plastics. My name is Matthias de Monte from Robert Bosch, and I will guide you through this video. This presentation is the result of a collaboration between Bosch, Hexagon Extreme, and Sintratec, and has been developed within the publicly funded project BMAP. The outline of the presentation includes an introduction, a block on 3D printing of plastic parts, a block on simulation of the printing process, and a summary and an outlook. The components considered in this use case were support parts for the production line and customized sensor housings. The demonstrators considered were a sensor carrier plate and a warpage plate as depicted in the pictures. They were made of polyamide 12 by SLS laser sintering. The objective of the project is to achieve first-time right production by minimizing warpage and initial stresses in the simulation phase. The selective laser sintering process is a process suitable for small series production of parts which need high customization. Referring to the simulation chain for 3D printed plastic parts, the situation at project start was that the printer parameters had to be manually taken over in the process simulation. There was no possibility to consider the actual laser path used by the printer. In particular, no interface was available between Sintratec printers and the software Digimat AM. Why is the laser path so important for 3D printed parts? You can see here how samples extracted from a crucible specimen at different positions result in strongly different mechanical behavior. The sample 1, presenting a short vector length, behaves about 30% stiffer than sample 2, which had a longer vector length. The laser vector length is thus strongly affecting the mechanical behavior of the part and needs to be considered in the simulation of the printing process. The 3D printer used in this project was the Sintratec S1, which is a printer in the low price segment and an easy-to-use one. The maximum print volume, which is the size of an object, is of 13 times 13 times 18 centimeters. The laser power is 2.3 watt and the laser wavelength 445 nanometers. It can accommodate a powder capacity of 7 liters and it can print up to speeds of 20 cubic centimeters per hour. Here you can see the warpage demonstrator considered in this project. The warpage specimens were printed on a Sintratec S1 printer at Robert Bosch, considering one specimen per build, and the material used for the printing was a PA12 in black color. This specimen was printed with different hatch strategies, referring to the direction of the laser path. As you can see in the slide, 3 strategies were used for specimens lying in the XY plane, which is the building plane of the building chamber, and the same hatch strategies were used with specimens put upright within the building chamber. I want to show you now how the pre-processing on the Sintratec S1 works. The first step is to upload a part geometry. Then you proceed in defining the positioning of the part within the building chamber. In the next step, the print parameters are defined. We select, in this case, custom parameters, and we proceed with entering a layer thickness, in this case 100 micron. Next, a hatch strategy is defined. We select again custom and enter an angle of plus minus 45 degrees. The angles are entered in radians in this case. We can further check if other parameters are okay and proceed to the preview. You can see here how the laser part looks like for each layer. And indeed, we recognize the plus minus 45 degrees angle. This is a close zoom on the part. If you want to recognize the shape, you have to zoom out. In this mask, the position of the pistons for both the printer and the powder bay are defined. The first action is to define an increment of the movement of the pistons in millimeters. We can further proceed in setting the parameters of the temperature, both for the heating up process and for the chamber during the printing. The last step is to choose the laser speed. Before starting the printing job, you could also define some scaling parameters for correcting warpage and shrinkage of the part. This done, the printing job can be started. In this video, we can see how a printing process on the Sintratec S1 proceeds. The built-in chamber is protected by a metallic grid, and you can see the proceeding of the lasering beyond this grid. A warpage plate is printed with a hedge angle of 45 degrees from the left to the right. The temperature of the layer is being actively controlled by infrared lamps, which modulate accordingly their intensity. Once the sintering layer is completed, the laser proceeds in refining the edges until the piston prepares for application of the next powder layer. This slide is showing the interface developed within the VMAP project, enabling the transfer of information from the 3D printer to the process simulation software. This interface, which was not available at project start, allows to consider the actual laser path together with further printer parameters in the process simulation.
Hello, this is Olivier Lietard from Extreme Engineering. We are going to review together how SLS process simulation can be performed in DigimatAM. In this video, we can see how the pre-processing in DigimatAM works. The simulation follows the physical printing workflow, and we first need to select the process, SLS here, and then the printer, where we can select the Sintratec S1 printer. Then we will be able to select the geometry. So this is the warp plate under an STL file format and define the material. This is the PA12 powder provided by Sintratec in the Digimat MX database. Then the next step will be to define the process parameters. We have been able to create an interface with Sintratec pre-processing software to load the laser pass in DigimatAM as is illustrated here. So the laser pass in red is superimposed to the geometry. We can also animate the laser pass to check that it's correct overlaying with the geometry. Then we can also fine-tune further some of the process settings, such as the chamber temperature. Then we also have the laser power, the scan spacing, and finally the laser speed. Further to this step, the simulation is set up. So the part is meshed with a voxel mesh of 0.5 millimeters made of voxels. And then finally, we can go to the job submission tab, where we can select the number of CPUs and finally submit the job. Once the simulation is completed, the results can be analyzed. On the left, you can see the animation of the SLS build with the part and the powder, and the part is depicted in black. That allows you to have a very good insight of what is happening inside the chamber. On the right, we have the deflection of the part that is illustrated layer by layer. The other typical results can be processed, such as the residual stresses or the crystallinity. And in particular, the results can be exported to another software to, for example, take the residual stresses into account in a static structural simulation. Once the exported results have been exported, they can be imported within Digimat Map for further processing. So here in this case, we are uploading the DigimatAM voxel mesh and also some of the results. So this is the finite element mesh that was used by the process simulation. And then we can also, for example, load the residual stresses that have been exported. So this is what is done here. And we will also display the first component of the stress. And once this is done, we can export these data under the VMAP file standard for interconnection with any other softwares.
The simulations in DigiMat.am considering the laser path can also help to explain the difference in mechanical behavior between different vector lengths. Referring to the cruciform specimen already considered, you can see that the vector length in the sample 1, which is the shorter one, presents a higher temperature peak compared to the sample 2 with a longer vector length. The higher temperature peak will result in a better melting behavior of the powder and thus a better consolidation of the material. Hence, higher mechanical properties are resulting. Comparing the deflection along the z-axis, we can see that the laser path has a significant influence on the deflection itself. In particular, the hedge of 45 degrees shows the strongest deflection. A comparison between the simulated warpage and the experimental one was done by analyzing with CT scans the warped parts out of the printing process. As you can see in these two pictures, the qualitative deflection of the part is well in accordance. However, the accuracy of the warpage prediction still has to be improved. Finally, coming to the expected benefits of the project. The establishment of a reliable simulation chain will enable the first right-time production of additive manufactured parts. Considering the laser path in the process simulation was implemented for the first time. Further, an improvement of the accuracies of the simulations was achieved thanks to a transfer of the printer control parameters to DigiMat.am and an advanced material characterization and modeling of the PA12 powder. Having the Syntratec printers in the printer database of DigiMat.am and adopting the VMAP standard was further enabling an easy data transfer and an easy exchange of CAE tools along the simulation chain. Additive manufacturing simulation is, however, still a low maturity stage, and some challenges need still to be addressed, as improving computation time, considering multiple parts within one build, and ensure the consistency of shrinkage parameters between printer and simulation code. Thank you very much for your attention.